In this video, we're going to extend our approach of the left and right sums for estimating integral values. We have those as a way to approximate definite integrals, but they're pretty crude, and the key word for numerical method people is that they're inefficient. It takes a lot of work to get a fairly high accuracy. It's also worth knowing that while we took these as a springboard to get to our integrals, and moving forward, we would love to be able to just evaluate integrals and do them exactly with calculus and some fancy skills we're going to learn over the next few units. However, there's some cases where we're not going to be able to evaluate these integrals. One example is a very famous function, e to the negative x squared. That graph is our bell curve. That shows up in probability, statistics, physics, all over the place. But it turns out none of the techniques that we're going to learn later can be used on e to the negative x squared. We have to estimate the integral for that function. There's also many other functions, many other famous functions used in science, physics, chemistry, biology, that also don't have integral values. Sine x over x is another one. And in those cases, we are going to have to use estimate approaches. But can we improve on left and right? Because they're really not that great. Let's see what we can do. Our first thing to note is that we can always use more rectangles. If we use more rectangles, subdivide more finely, if we're willing to do more work, then we can get closer and closer estimates, even with the left and right hand sums. However, we're hoping that there's a way to be more efficient about this. In other words, get something more accurate for similar amounts of work. Our first stab at this is going to be the midpoint rule. The motivation here is that if we look at a function like this, and we contrast what we get when we look at the left-hand rule, let's do this with 3 big intervals here. Here we go. The left-hand rule, or the left-hand sum, is represented by the area underneath these rectangles. For the right-hand sum, if we divide it into 3 intervals again, if we use the right-hand endpoint for our heights, we get these rectangles. And what we see is large swaths of missing area in this sketch here. And in the right-hand rule, we see large swaths of extra area that we don't want. Well, if we take a Goldilocks perspective and say, well, why don't I, on each interval, instead of taking here what ends up being the lowest point or the highest point, why don't we go to the middle of the interval? That's probably somehow more representative. Go up to the graph there and build a rectangle. What we get from that is we have a little bit of overestimate, but we also have a little bit of underestimate, and those are going to be pretty close to each other. So in fact, there's an error on both sides that's going to cancel out. And if we do the same thing on the next interval, go to the midpoint, go to the graph, and draw a rectangle with that height, again we see we're missing some area here, but we also have a bit of extra here, and so on average we're going to be pretty close to the actual area under the graph. Certainly much closer than these monotonic estimates like the left and right. Certainly at first glance here, it appears that the midpoint rule will be more accurate. And notice we would get something more accurate by just being more clever about how we build our heights. We're still going to use 3 rectangles, so we're still going to do 3 height times width calculations. And that's what we mean by efficiency. Same amount of work, but higher accuracy, almost for free. It's also worth noting what kinds of functions you would actually get the exact answer for. If you think of the midpoint rule and going up to the height and building it across, certainly a constant function would give us an exact height. That's true for the left and right hand rule. Another kind of function that's going to give us exactly the same area as the area under the graph would also be a straight line. If we imagine a straight line, let's make this a little more even looking here. There we go. Then the overestimate that we get from the midpoint rule is going to be exactly balanced by the underestimate on the next part. And so for linear functions, the midpoint rule, or the midpoint sum, is going to be exactly equal to the integral. So that's already progress compared to our left and right. The left and right rules only worked perfectly if the function was totally flat. You'll have some exercises on this in the practice problems, but we also have another technique that we'd like to explore as well. That'll be in the next video.